optimization problems in economics, which we will do today. At the end of the class today, Professor Nayak gave some very interesting examples of the use of AI in economics. And in fact, some of them are, for the traffic management and the city brain. There's a new project called the City Brain, where it does all this information gathering. Then for criminal and police investigation, there is a full architecture. So maybe at the end of the course somewhere, if we get time, I will give you examples of how for the whole of the integrated rural development, what sort of AI platforms can be developed. I think what we'll do is I will take a short lecture at the end of this module or at the end of the course sometime, or then we can finalize. Then we can give some good case studies, end-to-end case studies about these examples. So we get back to our basic problem, and our problem is that in order to solve problems, we were discussing the state space definition, where we had a state or a configuration, state transformation rules, which define that implicit state space graph, initial and start states and goal state solution. Now we are going to add what are called heuristics or domain specific knowledge. And very quickly, we are going to see some of the interesting heuristic search algorithms. After we see the basic algorithms, then one day we will go back to all these complex policy design scenarios that Professor Nayak and Professor Pulak Mishra mentioned, and see how to model. But before that, let us go and get a hang of the basic methodology. Once we know the basic methodology, how to convert any such problem into a state with state space rules, how to model the objective single or multiple, how to model the parties single or multiple, and how to model the dynamics of that situation. We will come to it. So we have seen the traveling salesperson problem the other day, and we also discussed that how a heuristic can be defined. For example, we said that if we are say at ABE, then we have visited sequence A, B, and E. So we have started at A, gone to B, and now we are at E. So how do we find the best remaining distance and a lower bound, because this is a minimization problem. Sorry, this is a minimization problem. So we need to find a heuristic estimate, and one heuristic estimate was that if it is ABE, we remove B from the graph with all the edges and then try to find the shortest path from E back to A. It may go through one city, it may go through two cities, it may go through all cities, and that will be an underestimate. There are others which we discussed. Let us come to the problem that we have at hand. We have a set of problems at hand. One problem says that we are given a piece of resource, R. We have n bidders, each giving an option saying that I require so much, will give so much of return. And we have to allocate R to some of the bidders so as to maximize the total return. The first variation that we can give to this basic problem is that each bidder gives an ordered set of options. That means they say that if you give me R1, bidder 1 says, if you give me R11, then I will give you return E11. If you give me R12, this is for bidder 1, E12, and so on and so forth. So this person gives an ordered set of options saying that this is my order of preference. And what we have to choose is we have to choose one of them from this ordered set of preferences. We could again make the problem a little more variant. We could say that instead of one resource, we have got K different kinds of resource, like the K departments, the Manrega, all these things that he was talking about. We'll map them later. And then they give an ordered set, and here instead of just saying how much I require, so it would say for this resource, this is my requirement. This is the capital investment that I will make, and this is the return. And then one bidder can be given at most P allocations. A bidder may limit to a single. This word is single. A single bidder's return can be limited to P. A single bidder may have a total capital which is limited. So as you can see, we can start making the problem more and more complicated. And just instead of resource, we can go to policy, we can go to every other kind of problem and map it that way. Then a bidder may also say how many people I will employ. Then we may ask that you have to optimize the total return and the total employees. And last day we talked about this multi-objective function, non-dominated set, and the Pareto optimal set. The other final thing is when these multiple bidders who are multiple players don't give all their bids upfront. So it is by auction, one by one, people start bidding. So once you make a bid and something is done, then everybody gets a chance to bid again. So and each bid works like an auction. So you can model all of these problems, as I just said. All these problems that we talked about can be modeled by state transformation rules, start, goal, objective function, what am I trying to do? Minimize, maximize, multiple objectives, and then it can convert to a sequential game. The sequential game situation will come when there are multiple parties bidding for auction. Then it can also come in terms of an adversarial situation where we have probabilities on the state transformation rules. And many of the solutions that you find, sometimes you find a full solution from start to goal. Sometimes when there are probabilities and just examples which you took where you have a policy, you ask for options. You say that I'm going to do this. Then you ask for feedback. Based on the feedback, you take the next step. So here it becomes a continuous process where you may not do the planning till the end. You look ahead till the end and then you take one step and see exactly what is the outcome, because the outcome is probabilistic. You have looked ahead, this may happen, that may happen, etc. And then you've taken one step to see what exactly goes happen. So all these problems can be mapped, but for the time being, we are going to solve the basic problem so that we understand the solution. Our basic modeling is the state transformation modeling, and our basic solution will be a search solution. So let us look at the first problem and then we will come to what we want to do. So how do we solve the problem? So what are we given? We are given a state definition, a set of state transformation rules, a start state, and a goal state, and an objective function. And we are to find the best path from start to goal through these state transformation rules. Is everybody with me? Is everybody with me? Anybody has a doubt at this point in time?
No, sir.
Okay. So what we do is, because once we understand this thing clearly, then all complications will be taken care of. We create two data structures, simple data structures, which are lists. One is called an open list and one is called a closed list. because we have only the start state. We have not the graph, because the graph will be generated by the state transformation rules. And we have these 5 steps: initialize, select, goal test, expand, and continue. What we do is we initialize the open set with the start state, and the closed set is initially empty. Now at every point in the select, there may be many nodes which are states in this open set. We will choose somebody from the open set. If there's nothing in the open set, we terminate. Once we get somebody in the open set, we choose somebody in the open set. How we choose, what we choose, all will depend on the algorithm, and all our algorithms will depend on that. It depends on the problem, objectives, we'll come to it. Then you check, after you have removed a node from open, you check whether that node is a goal node or not. If it is a goal node, that means you have found a path from start to a goal node. So now you have found a path. So either you can stop, or if this is not the optimal path, you can continue. If it is not a goal node or you have not stopped, then now you have a node N which you have extracted out from open. This node is only a state, an intermediate state from start to goal. Now you generate its children using the state transformation rules. And the children, and you put N now enclosed. Now the children could already be in open or closed, or the children could be new. They are neither in open nor in closed. If they are new, then you will compute this heuristic evaluation function for every node Ni. Because this heuristic evaluation function will be used in the select step. We'll see examples one by one. Will be used in the select step. This heuristic evaluation function will be used for solving the problem. We'll see detailed examples, but today we just go through the algorithm, then we will see detailed examples. Once you have generated, it's a new node, you compute this and put it in the open list. This is a new node. This is for this part, 4C. If it, and you put it in open, so it goes back to open. This new node goes to open if it is a new node. If it already exists in open or closed, then you will check whether you have come to it with a better cost or not. If you have come to it with a worse cost, you do nothing. If you have come to it with a better cost, you improve. So now you have put new people in node open. You have put the old people, some old people in closed. You go back to step 2, and you go on doing this till you find the goal node or open set becomes empty. This is the basic algorithm. Now let us see how you solve. What do you do for a minimization problem? For a minimization problem, you compute at every node 2 values, Fn and Gn, Gn and Hn. What is Gn? Gn is equal to the cost. This is a minimization problem of the minimum cost path from S to N, cost of the minimum as of now. So whatever I have seen till now for this node, so if this is N and this is S, then depending on my search, this is the cost of the minimum cost path from S to N, and Hn is the estimate of the cost of the path from N to goal. So what is Hn? Hn is the estimate of cost of path from N to goal. So we will now compute Fn is equal to Gn plus Hn, which is called the evaluation function. And this evaluation function gives me an estimate of how good this node is amongst other nodes. So now we will do these 5 steps. We will initialize open list with the start node. GS is 0, FS is HS because GS is 0, closed is empty. Then we will select that node from the open list because we are solving a minimization problem with minimum Fn. If open is empty, terminate with failure. If n is a goal node for a minimization problem, and for the assumptions that we will make that the heuristics are underestimates and monotonic, you don't need to bother about it now. We will stop and say this is my solution. If it is not a goal node, then you will generate the children, put n in closed. For every new node, you will compute the value of GNI. So from n you have created a node Ni. This is the edge cost NNI. You will compute GNI is equal to Gn plus CNNI. Once you have computed this, you will check if it is a new node, then that is fine, you put it in open. If it is an existing node, you check whether you have come to it with a lower cost. If you have come to it with a lower cost, you update GI and therefore FNI gets updated. Otherwise, you do nothing. Based on that, you have now reset your nodes and you will start again. Go back to step 2. This is called algorithm A star. It is a best first search algorithm. Let us work out an example that will make the working of the algorithm clear. So suppose this is my graph. And suppose this is a minimization problem. I have got my start state. My state transformation rules create this graph. This graph is not given to me directly. On every edge, I have the edge cost. The red values at every node, like A, I have 6, B, I have 5, C, I have 4, D, I have 3, E, I have 9, F, I have 3, G, I have 1, H, I have 3, I have 0, and J, I have 0, are the heuristic estimates. So these are the HN values. So initially, what happens? My open list consists, so if my open list is like this, and my closed list is like this, in step 1, my open list contains A and my closed list is empty. So that is what is depicted here. And then the Gn value of A is 0, the Hn value is 6, therefore Fn equal to Gn plus Hn is 6. My algorithm has these steps. I want to write it down. Initialize, select, goal test, expand, and continue. Now, since open is the only node, in the next step, when I come to select, open will go to closed, and who will come to open? Can anybody tell me? What are the children of this node?
B, C, and D.
B, C, and D will come to open. Now when B, C, and D comes to open, as I have listed here, B has got G value 10, H value 5, F value 15, and its parent is A. C has got G value 12, H value 4, F value 16, parent is A. D has got G value 5, H value 3, F value 8, parent is A. Now we come back. So after it, we have generated. So once we selected A was not goal in step 3. Then we expanded A to generate children B, C, D, put them in open, went back to step 2. Now in step 2, by algorithm A star for a minimization problem, which node we will select?
D.
Which is the minimum F value?
D.
D. So D will be selected. Once D is selected, what is put in open list?
Sir, B, C, G, H.
G and H.
Very good. And as you can see, once G and H is put, G value is 11. It is 5 plus 6. H value is 1. F value is 12. Parent is D. For H, it is 9, 3, 12, D. Now I can select which one, either of G or H. Isn't it? Now I go back and I will again select somebody from open. I can select either G or H. Let us say we can select anyone. Let us say we select H. If we select H, then what happens? What happens? Who are the children of H?
None.
None. There are no children of H. There are no children of H. So what happens to open? B, C.
It will become MPT like B, C, G only.
B, C, G. Now who will be removed from open?
G.
G will be removed. Very good. And B is there, C is there. And what will be entered into open?
J.
There is H, but
J.
there are two children of G, H and J. J will be entered. And what will happen to H? You are coming to H with a larger G, isn't it? The current G value of H is 9. And now you are coming with 11 plus 13, isn't it? If you come from node G, then the G value will become 13, no point. Now which node will you remove? Because these two, what is the F value of J? G is 14, H is 0, and its parent is capital G. Which value will be, which node will be removed?
J.
J. And what will be satisfied?
Our goal.
J is the goal
Goal
state.
test. And you will terminate. Have you understood how the algorithm works?
Yes, sir. Sir, just one question. How are the H estimates are calculated?
As I said, the H estimates are calculated for every problem. We will come to some problems and calculate their H estimates. We'll do that. First, understand the algorithm. Let us okay. Let us go back and understand how to calculate H estimates. Let us do this problem. This first problem. This first problem, you are given a set of resources. So you remember how we had created a state? How was a state defined? In this problem, first problem, how was a state defined? Some choices have been made, B1, B2, some BK choices have been made. You remember? Some are remaining to be made. And so much has been allocated A, so much is remaining R. This is a state. And at every point in time, you will take an element from this node and either select it or not select it. Didn't we do this last day?
Yes, sir.
Yes, sir.
So now at a particular state, how your G value here is how much of the profit you have to made, right? How will you compute H value? If you have to maximize, you will compute an H value. So what can you do? You can sort the return. So you will do a return by requirement ratio. This is the density per unit return that the bidder gives. Got it?
Yes, sir.
Then you will sort it. You will sort the remaining bidders by this ratio. And you will choose it in this order. Then if the last fellow which overtakes, you will only choose proportional amount. So if there is a remaining amount, you will only choose a proportional amount, but you will use this ratio for that proportional amount. Whatever unrealistic it is, it will give you an overestimate, isn't it?
Yes.
So similarly, you can compute heuristics for all the problems. So once we have understood how minimization works, let us quickly understand how maximization works. In maximization again, we again have our heuristic estimates. Same thing. We only remove a node in open of, instead of removing the node with minimum Fn, we remove the node with maximum Fn. And whenever previously the rest of them are all same except this part where you were coming to an already existing node. You were coming to an already existing node. Previously, you were updating the cost if you came with a lower or larger in minimization.
Sir, with a lower cost.
Lower cost. Now you will update it when you come with a
Higher cost.
higher cost. Pakka, 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 pakka. Got it? Let's work
Yes.
out the example. Our steps are again initialize, select, goal test, expand, and continue. Good. So now initially my open consists of, so let us do this. While I have done it there, but if we do this ourselves, it will become much easier to understand. Initially in step 1, open consists of which node? A. In step 2, again, which children are generated? B, C,
B, C, D.
A is enclosed. And again, I have now drawn new heuristics because for maximization we need overestimates. So now we have B is 55, so its F value is 65, C's is 56, and D's, which node will be removed?
B.
B.
B. Very good. And what will be put as children?
EFG.
E, F, G. Very good. Now once we have EFG, E has got 37, F has got 46, G has got 28, C has 56, and D has 38. Which will be removed?
C.
C will be removed. D, E, F, G are there. Now what are the children of C?
F and G.
And F and G already exist. Are you coming to it with a larger cost because it's a maximization problem? Current value, G value of F is 17. And now you are coming with
with the
12
higher
plus
cost.
7. 12 plus 7 is 19, isn't it?
Yes, sir.
So now you are coming with, so in earlier it was 17. Now you are coming with 19. So you update this cost, nothing else. For G, your earlier cost was how much? Oh, but G, yeah, G.
16.
Yeah, your earlier cost was 16 and your new cost is?
17.
Correct. So new cost is 70. All you have done is updated your costs. Now which node will be removed? 37, 48, 29, 38. Which will be removed? F.
F.
So D, E, G, A, B, F. And what are the children of F?
E, I, G.
E, I, G. E and G already exist. Will their costs be updated?
Yes, sir.
So E had its initial cost 18. Now E's new cost becomes 28.
Then
G's earlier cost was 17. Now it becomes 20. And I's earlier cost was I there, or I is a new node generated now.
rise a new node. Sir, E's
I
cost would be 26, right?
huh?
E's cost would be 26. 10
By
plus 7 plus 9.
huh? 12 plus
Sir,
7 is
E
19 plus 9 is how much?
12 plus 7, 17 plus 9 is 26.
12 plus 7 is not 17, no?
No, sir. 10 plus 7 plus 9.
No, but its current G value is from A to C to F, no? That is 12 plus 7, है ना?
Oh, okay. I was considering it from A to B to A.
नहीं, हमारा तो update हो गया वो F का F value
Yes, sir.
has been updated to 19 already in the previous
Yes, sir.
iteration. ठीक है? So now it becomes
Yes, sir.
28. Now which node will be removed from D, E, G, I?
Sir, I.
I will be removed.
Sorry, E.
What is the F value of I? 37. What is the F value of E?
Oh,
46.
sorry, sir.
E will be removed.
E will be removed. So from in the next step, E will be removed. A, B, F, E. And
Sorry,
D
sir,
remains.
it should be A, B, C, F, E.
ABC,
Yes, sir.
yes. ABCFE, 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 pakka. And now, what is the children of this person E? I and J.
J.
J is a new node. J is a new node, but I, what happens to I? Its existing, what was its existing H value? G value was 37. Now what will it become? Existing value which came from F was 37. See, it was 12 plus 7 plus 18. Correct?
Yes, sir.
Now it will be from E. So it will become 46. Because E's current cost is 28. 28 plus 18, 46. Now, which is the largest node in Open?
I.
I. And I is a?
Goal
Goal
state.
state.
So you will add it. And since we have maintained who is the parent of whom, we now know how to go back to start. So these are the two variations of how you can use heuristics to solve maximization and minimization problems. Now let us quickly, before we terminate this class, I didn't want to take too much time. Let us look at the properties. If the heuristic estimates are non-negative lower bounds for minimization problem and non-negative upper bounds for maximization problem, monotonic, and the edge costs are positive, the first solution is optimal. Then there are other properties, but at least this much is very clear that the first solution is optimal. Now, what we will have to look at are 3-4 things. One is, how do we model other problems? Second, how do we develop heuristics? Third, what about real-time algorithms? Fourth, what about multi-objective? And fifth, what about multiple parties? These are our questions. But having understood this algorithm, basically having understood these 5 steps, all the algorithms that we shall discuss will be based on these 5 steps. And variations of these 5 steps will yield us all the algorithms that we are interested in. And then we will have to do all of these things. So tomorrow when we take our class from 2 to 5 p.m., we will look at all these variations and see how versatile heuristic search is to model such problems. Then we will look back at our problems of these types and see how we can convert many actual problems. This resource problem of variation 2 is a standard problem, whether you talk about the farmers, their discussion, whether you talk about portfolio in a bank, whether you talk about policy design, all problems can be mapped to this generic problem. This generic problem can be mapped to a state transformation problem with objective functions, and these can be mapped depending on our requirement to a heuristic search problem. Multi-objective, real-time, fast, optimal, everything. This is the heart of search. And tomorrow we will start with some more interesting algorithms, having seen the basic algorithms. Any questions? We'll stop today, but if there are any questions, I'll be happy to answer them. And tomorrow we'll see variations of these algorithms for other. At the end, after we have studied all the algorithms, then at some point in time, we will look at the problems and then start mapping the problems into state description and heuristics. After that, the algorithms are known. Any questions? Was it understandable? Please go
Sir,
through the video once, it will become easier.
hello,
Akshat,
sir.
were you saying something?
Yes, sir. In the last one, sir, when we have find the when we have a in the last one, so when we have A, B, C, F, E in the close node in the close, then how our computer will know that we have gone from A, C, F, E, I, not A,
देखो
B,
ना,
C.
look at node I. I में क्या क्या लिखा है? 46, 0, 46. After that, what is written?
Okay, sir, I got it.
Parent. We
Yes,
have
sir.
maintained parent pointer.
Yes, sir,
The
I got
best
it.
parent. Isn't it a very interesting algorithm? Very simple, very straightforward.
Yes,
And
sir.
it works. Behind all your Gurobi, Murobi, all these, everything, only this algorithm is there. Behind all your great optimizers, only this algorithm is there. Some variation of this algorithm.
Sir, why the first solution is an optimal one?
There is a proof for it. There is a proof for it. You want to know the sketch of the proof. Let me tell you. Suppose we are solving a minimization problem. Okay. Now we have these 5 steps. Now suppose you are, let me argue with you that no, I have found a solution, but this is my first solution is not minimum. Good. Now you have selected in step 2 the minimum node in open for a minimization problem. So suppose I have terminated with goal G1 and its solution cost is FG1. Now in open list, the actual node N which leads to the optimal goal G2 exists now. Because the search has proceeded, some other node exists. But I have terminated with G1. Is that okay with you? Are you okay with me up to this step?
Yes, sir.
Now, what is the F value of N? If the final F value of G2, if this is the final F value of G2 and the heuristics are underestimates, then this will be less than or equal to F of G2. Correct? Yes or no?
Yes, sir. Yes, sir.
If this is less than F of G2 and if G2 is the goal, then we also know that F of G2 is less than F of G1 because G2 is optimal and G1 is not. Correct?
Yes, sir. Yes, sir. Got it.
So then we have selected the minimum node from open. How come we selected G1 when N was there? Proof by contradiction. Got it, Aman?
Yeah,
Who
sure,
had
sir.
asked? Yeah, good. So just brush up these algorithms. Look at this video. It's a 20-minute video. I will try to share the slides. Tomorrow we'll just quickly revise this and move on to the other algorithms which are real time, low memory, fast algorithms. You know, all these algorithms, this algorithm becomes simulated annealing. This algorithm becomes something else. All of these algorithms become our other algorithms. All the famous algorithms generate from here. Okay then. Any other questions? Otherwise, we'll stop for today.
Sir, a Google form has been toted to fill us for assignment 1. Sir, do we need to fill it individually or in groups?
Individual.
Okay, sir.
Is that true? No, individually though. Our
Yes, sir.
individual.
And so one thing more, sir, like I am not able to open the form. It's telling that it's needed request access.
So maybe you have a problem with your email ID. The email ID.
Sir, I have registered the
You talk to the TI. I have no knowledge of this.
Now in the MS Teams, that link is posted, or even in the chat box, I can post it, sir.
No, he's saying that he does not have permission to update that form. That is what he's saying. Can you stop the recording at least? Then we
Yes, sir. Yes, sir.